In the last few years, a new paradigm has emerged in theoretical physics. This paradigm seeks to understand space-time structure through concepts from quantum information. For example, one studies the interplay of geometries and entanglement entropies and tries to understand in particular the emergence of geometry from universal entanglement properties of quantum systems.
In our paper, we ask a different kind of question, but still within the same paradigm. We ask, is there a quantum origin to the local symmetry group of spacetime? In other words, can we understand the Lorentz transformations from a quantum information perspective? Now, the Lorentz transformations have an inherently operational interpretation, namely they translate between different reference frames. And as such, they translate between different descriptions of the same physics.
But the physics that all observers describe is ultimately quantum in nature, and therefore it is natural to ask, if we have different observers describing quantum physics, how can the descriptions differ, and how can these different descriptions be related? The key point is that we ask this question without assuming a specific space-time structure, and in particular we do not assume what the signature or even dimension of space-time is. We only assume the validity of quantum theory in the local laboratories of observers.
In our paper, we then actually derive the Lorentz transformations of 3 + 1 dimensional Minkowski space in this framework, under certain assumptions. Now, what are these assumptions and how do we achieve this? We have two observers, Alice and Bob, in their local laboratories who have never met before but can communicate. We consider the following task. Alice asks Bob on the phone to send her a specific quantum state. If they have never met before, they will describe quantum states differently, and so Bob will not know Alice's choice of basis, and he will send the wrong quantum state. For any specific quantum system, for example an electron, Alice and Bob can synchronize the descriptions. For example, by sending a complete basis of states, they can find a transformation, let's call it T, that translates Alice's description into Bob's. This synchronization allows them to win the game.
But do they have to repeat the synchronization for all kinds of quantum systems? This could become an arbitrarily complex task because there may be infinitely many different kinds of systems, and a priori, the synchronizations for different kinds of systems could be unrelated. But we know from experience that this is not the case in our universe. The synchronizations for all systems are related. We therefore ask, how can one understand this empirical fact from a quantum information perspective?
We identify a new concept that offers an operational account for this, the concept of universal measurement devices. Such a device allows an observer to measure a fixed observable on different kinds of quantum systems universally. For example, think of a Stern-Gerlach device that measures the spin of different kinds of particles. The key benefit is that these devices allow observers to transfer the synchronization of one kind of system to another. We show that if there are sufficiently many universally measurable observables, then Alice and Bob can synchronize their descriptions of all quantum systems at once. And if certain consistency conditions are satisfied, we show that this gives rise to the Lorentz group.
So how do we interpret this result? Have we now re-derived special relativity and the dimension and signature of space-time? Not directly, because our setting does not by itself yield an immediate geometric space-time picture. However, the result is very suggestive of a space-time interpretation because, after all, the local symmetry group of space-time is nothing but the dictionary between different observers' descriptions of physics. Our paper therefore does propose a new quantum information perspective on the origin of the local symmetry group and thereby the dimension and signature of space-time. And this is what we seek to exploit in further work.